Hello, we are Group US Silica and this is our Capstone project. Now, the members of our team are Brent Beck, Sarah Ploner, Nan Gan, Cindy Coy, and Brian Swift. And in this, we'll be covering waste heat recovery for US Silica. Let's get into this. Our project stems from a past energy audit of U.S. Silica Middleton plants by the Pennsylvania Technical Assistance Program, or PennTAP for short. It was identified that using ambient temperature air in their drying system was causing elevated natural gas consumption during the winter months. It was suggested that a waste heat recovery system to be implemented to reduce the cost and emissions. This has since become the problem, and our group was challenged to solve it. It was made clear that this design's main goal would be to reduce the natural gas consumption, have a practical economic return, and to not disrupt or reduce the quality of the current operation. To be considered for implementation, our design had to be safe, financially feasible, passive in the current system, and efficient. These qualities guided us through our brainstorming process and concept evaluation. A visit to the plant was key in developing a general idea in how we could recover waste heat from the system. After this visit, 4 main ideas were created as seen in the flow chart here. Using the key qualities previously identified, it was determined that passing the exhaust air through a heat exchanger was the most viable option. We then proceeded to model the system using an energy balance and evaluate the true potential savings that can be attained. The figures created below summarize the reduction in heat load. It was determined that preheating the fluidized air by 30 degrees Fahrenheit would be an appropriate goal, resulting in over $28,000 of savings per year. Next, the proper placement of the heat exchanger was determined so that it could conduct the hot exhaust air and the cold inlet air at the same time. The best placement is modeled here, which establishes some rough dimensions constraints. The preheating goal in place and some rough dimensional constraints, the actual heat exchanger could be selected and properly sized. With these factors in mind, a single pass shell and tube heat exchanger was selected for its ability to effectively handle corrosive and abrasive fluids. The required heat exchanger should consist of 1,682 steel tubes of 3/4 inch diameter and a 10.5 foot length. Several future steps were recommended to US Silica to further improve the accuracy of the created model, and an alternative suggestion of a compact heat exchanger was identified. This design and model improvements could potentially result in a better performance and project economics. While the exact design synthesized here may not be implemented, we feel it illustrates the future feasibility of such a project by accomplishing the project's goal. It was estimated to reduce natural gas consumption by over 3,000 MCF, reduce CO2 emissions by 185 tons, and save $28,000 annually.